In this episode, we explore the early days of chatbots, focusing on AIML Artificial Intelligence Markup Language and NELL Never-Ending Language Learner, two pioneering systems in natural language processing NLP. We dive into the mechanics behind AIML's rule-based architecture and its pivotal role in powering early chatbots like Alice. We then contrast AIML with NELL's self-learning capabilities, discussing how NELL continuously expands its knowledge by analyzing vast amounts of internet data. The episode also covers advanced techniques such as word embeddings, model merging, and the challenges of deploying NLP models in real-world applications, including security concerns and the importance of structured outputs. Finally, we look ahead to the future of AI, discussing adaptive schema evolution and the integration of external knowledge bases. Buckle up, this is going to get deep. Enjoy the show.
Today, we're going way back to the early days of chatbots, a time before Siri or Alexa. Get ready to explore AM and NL, two pioneers in natural language processing. They may not be household names, but they've definitely shaped the landscape of how machines understand us.
What's so fascinating about these two? They represent totally different approaches. AML, developed in the late 90s, is all about carefully crafted rules. It's like building a chatbot with a set of instructions. If this, then that. NELL, on the other hand, it takes the opposite approach. It's been learning on its own from the vastness of the internet since 2010. Just imagine that. A computer program constantly reading, making connections, and expanding its knowledge.
It's like a digital Sherlock Holmes, sifting through clues and building its own understanding of the world. But let's start with the OG chatbot architect,
AML.
Artificial Intelligence Markup Language. What was the thinking behind its development?
You have to remember, in the 90s, the internet was still relatively new, and the idea of a computer that could hold a conversation, that was mind-blowing. AML was designed to be simple and accessible way to create these early chatbots, essentially giving them a set of rules to follow so they could respond to human input.
And it worked. AML powered a chatbot named A.L.I.C.E., short for Artificial Linguistic Internet Computer Entity. And get this, A.L.I.C.E. actually won the Loebner Prize in AI 3 times.
The Loebner Prize, that's an annual competition. It aims to find the chatbot that can fool humans into thinking they're talking to another person. For A.L.I.C.E. to win 3 times, especially back then, it's really a testament to AML's effectiveness.
That's incredible. I'm starting to see why AML is considered a pivotal player in the history of NLP. But can you give us a peek under the hood? How does it actually work?
At its core, AML is all about patterns and templates. Think of it like a giant library of if-then statements. The if part is the pattern, a phrase or keyword the chatbot is looking for in the user's input. The then part, that's the template, the response the chatbot will give if it finds a match.
So for example, if a user types, "What is your name?" The chatbot would search its library of patterns for a match, find the "what is your name" pattern, and then deliver the corresponding template, which might be, "My name is Body."
Exactly. A simple concept, but surprisingly powerful. And here's where it gets even more interesting. AML uses wildcards to make those patterns more flexible.
Wildcards, like in a card game.
Sort of. In AML, wildcards are symbols that can represent any word or phrase. Instead of having to create a separate pattern for every possible variation of a question, you can use a wildcard to capture a whole range of inputs.
So if you had a pattern like "What is your A?", the chatbot could understand any question that starts with "What is your A?", regardless of what comes after. That's incredibly efficient.
It is. And it allows AML to handle a much wider range of human language than if it were just looking for exact word matches.
It's like teaching the chatbot to understand the intent behind the words, not just the words themselves. Pretty impressive for technology developed back then.
Absolutely. And on top of that, AML uses a concept called SRI, which stands for Symbolic Reduction in Artificial Intelligence.
Okay, that sounds complicated. What does SRI do?
SRI is like a shortcut. That lets the chatbot redirect to other patterns. For example, let's say you have a pattern for "what is your name" and another pattern for "what are you called." With SRI, you can tell the chatbot that if it sees the pattern "what are you called," it should treat it as if the user had typed "what is your name" and respond accordingly.
So even if a user phrases a question differently, the chatbot can still understand what they're asking and give a relevant answer.
Exactly. It's like teaching the chatbot synonyms and different ways of expressing the same idea.
It's amazing how these seemingly simple elements can be combined to create a surprisingly sophisticated system. But I imagine there were also limitations to this rule-based approach.
You're right. AML is very good at handling structured, predictable conversations, but it struggles with ambiguity and nuance. If a user asks a question that doesn't fit any of the predefined patterns, the chatbot is essentially lost.
That makes sense. It's like trying to have a conversation with someone who only knows how to follow a script.
Yeah.
You know, they're great as long as you stick to the script, but throw them a curveball and they're completely thrown off.
Exactly. And that's one of the reasons why researchers started exploring other approaches to NLP, approaches that could handle the messiness and unpredictability of human language.
And that brings us to NEL, the never-ending language learner. This is where things start to get really mind-blowing, right?
NEL is on a whole other level. Instead of being programmed with a set of rules, NEL is designed to learn on its own, continuously, from the vastness of the internet. It's been doing this since 2010, and it's never stopped learning.
Okay, I have to admit, the idea of a computer program, that never stops learning. That's constantly reading and expanding its knowledge. It's a little intimidating, but also incredibly exciting.
It is. Think of NEL as a tireless student, perpetually immersed in the world's largest library, the internet. It's constantly reading, making connections, and building its own understanding of how the world works.
So how does NEL actually learn? Does it just download information from the internet?
It's a bit more sophisticated than that. NEL uses machine learning algorithms to analyze the text it reads and extract meaningful information. It looks for patterns, relationships between words, and clues that help it understand the meaning of what it's reading.
So instead of being spoon-fed information, it's figuring things out on its own, like a human child learning to read.
That's a great analogy. And just like a child, NEL learns from its mistakes.
Wait, NEL makes mistakes? I thought it was like some kind of super intelligent AI.
Even the most advanced AI systems make mistakes. That's part of the learning process. NEL is constantly making predictions about the world based on what it's read, and then checking those predictions against new information it encounters. If its predictions are wrong, it adjusts its understanding and tries again.
So it's like a scientist,
Yeah.
constantly testing hypotheses
Yeah.
and refining their theories based on new evidence.
Exactly. And this continuous cycle of learning and refinement, that's what makes NEL so powerful. It's not just memorizing facts, it's building a deep, nuanced understanding of the world.
That's incredible. But how do we even begin to evaluate something as complex as NEL? How do we know if it's actually learning and making progress?
That's a great question, and it's one that researchers are constantly grappling with. One way to evaluate NEL is to look at its knowledge base, the collection of facts and relationships it's learned from the internet.
So it's like checking the student's notebook to see how much they've learned.
Exactly. NEL's knowledge base is constantly growing, and it now contains over 80 million beliefs. That's 80 million facts and relationships. It's extracted from billions of web pages.
80 million. My brain hurts just thinking about that. But what kind of information are we talking about? Can you give us some examples?
Sure. NEL's beliefs are structured as simple statements. Barack Obama is a politician, or London is the capital of England. It also learns about relationships between things. Michael Jordan played basketball.
So it's not just learning random trivia. It's building a structured understanding of how the world works, who the key players are, and how they're connected.
Precisely. And the more NEL learns, the better it becomes at making new connections and drawing inferences. It's like its knowledge is compounding, building upon itself over time.
Okay, I'm officially mind blown. But can NEL do anything else with this knowledge besides just storing it? Can it use it to reason or make predictions?
That's where things get even more interesting. NEL isn't just a passive repository of information. It can actually use its knowledge to reason about the world. It can make inferences, draw conclusions, and even generate hypotheses.
So it's not just a walking encyclopedia, it's actually using its knowledge to think and problem solve.
Exactly. And this ability to reason, that's what sets NEL apart from earlier AI systems like AIML. It's moving beyond simple rule following and into the realm of true intelligence.
This is incredible stuff. It feels like we're witnessing the birth of a new kind of intelligence, one that's not limited by the constraints of human programming.
It's certainly a fascinating and rapidly evolving field, and while NEL may not be the ultimate solution to artificial intelligence, it's definitely pushing the boundaries of what's possible.
So we've got AAL, the rule-based pioneer that paved the way for early chatbots, and NEL, the never-ending learner that's pushing the boundaries of machine intelligence. Two very different approaches, but both incredibly important in the history of NLP.
And both offer valuable insights into how we can build machines that understand and interact with human language.
It's incredible to see how far we've come since those early days of chatbot development. And it makes you wonder, what's next? What other breakthroughs are waiting to be discovered in the world of NLP? But before we get ahead of ourselves, let's dive a little deeper into the inner workings of NELL and AL.
I'm happy to explore the intricacies of these fascinating systems.
All right, let's start with AML. We talked about patterns and templates, but I'm curious to know more about how those patterns actually work. Can you give us a closer look at the mechanics of AML's pattern matching process?
Certainly. Let's break down how AML sifts through its knowledge base to find the right response. Remember those wildcards we talked about? They play a crucial role in making AML more adaptable and intelligent. AML's pattern matching. It isn't just about finding those exact word matches, it's more nuanced than that. Wildcards give you a way to represent a range of words, which makes the chatbot's responses more flexible, more dynamic.
Like those word puzzles, where you fill in the blanks to complete the sentence. The wildcards let AML understand, like, different ways of asking the same question.
Exactly. For example, you can have a wildcard represented by an asterisk, like this, and that can stand in for any number of words. So a pattern like, what is your ord, could match a huge variety of user inputs, like what is your name, or what is your favorite color, or even what is your opinion on the current state of AI.
That's really clever. So AML doesn't need a separate pattern for every single question that someone might ask.
Exactly. It's all about creating more general patterns that can capture the essence of the user's query.
But what if there are multiple patterns that could match the user's input? How does AML decide which one to use?
AML has a system for prioritizing patterns based on their specificity. So if there are multiple matches, it'll choose the pattern that most closely aligns with the user's words.
So it's trying to be as precise as possible in understanding what the user is asking.
Yes, and this is where another type of wildcard comes in, the underscore, me. Now, unlike the asterisk, which can represent any number of words, the underscore, that acts as a placeholder for a single word.
So a pattern like my favorite color is my favorite color is blue, but not my favorite color is red and blue.
Exactly. The underscore allows for more specific pattern matching when you need it.
So it's like AML is saying, okay, I know you're asking about your favorite color, but tell me, what is that color?
That's a great way to put it. And by using a combination of asterisks and underscores, AIML developers can create a very sophisticated system of patterns that can handle a wide range of those conversational scenarios.
It's like building a chatbot with a built-in understanding of grammar and syntax.
In a way, yes. AIML's pattern matching system, it's all about capturing the underlying structure of human language, even in its simplest form.
And then once a matching pattern is found, the corresponding template is used to generate the chatbot's response.
And those templates can be incredibly versatile. They can include simple text responses or variables that store information from the user's input. They can even have conditional statements that tailor the response based on the context, and even references to other patterns using that SRAY tag we talked about earlier.
The SRAY tag, it lets the chatbot redirect to another pattern. It's essentially saying, okay, I know what you're asking, but let me consult another part of my knowledge base for a more specific answer.
Precisely. And by linking patterns together this way, AML developers can create a really complex web of knowledge, which allows the chatbot to navigate a wide range of conversational topics.
Like building a chatbot with a mind of its own, capable of following different conversational paths and providing insightful responses.
While AML might seem simple on the surface, its ability to handle complex patterns and use redirection techniques like SRAY really demonstrates its potential for creating surprisingly intelligent chatbots.
Remarkable what early AI researchers were able to achieve with AL. It really laid the groundwork for the chatbots we interact with today.
It did. AML may not be as flashy or complex as some modern NLP approaches, but its impact on the field, it's undeniable.
A testament to the power of elegant design and a deep understanding of how language works. But let's shift gears a bit. Back to NELL, the tireless student that's been learning from the internet for over a decade.
NEL takes a radically different approach to language understanding, one that embraces the vastness and complexity of the web as its primary teacher.
It's like comparing a carefully curated library to the sprawling, ever-changing landscape of the internet.
That's a fitting analogy. While AML relies on handcrafted rules and patterns, NELL, it dives headfirst into that, chaotic world of online information, extracting knowledge from billions of web pages.
And as we discussed earlier, NEL's knowledge base now contains over 80 million beliefs, a testament to its tireless pursuit of knowledge. But I'm curious about how NEL organizes and manages all that information. It's one thing to collect facts, but it's another thing entirely to understand those facts and how they relate to each other.
You've hit on a crucial point. NELL doesn't just passively store information. It actively seeks to understand the relationships between the facts it acquires.
So it's not just memorizing random trivia, it's building a structured understanding of how the world works.
Exactly. NELL organizes its knowledge into categories and relationships. It connects entities like people, places, and things based on the information it extracts from text. It learns that Barack Obama is a politician, that London is a city in England, that Michael Jordan played basketball.
It's like NEL is building its own internal map of the world, with all the key players and how they're connected.
That's a great way to visualize it. And this structured knowledge base is what allows NELL to go beyond simple information retrieval and actually reason about the world.
We talked earlier about NEL's ability to make inferences and draw conclusions. Can you give us some more specific examples of how it uses reasoning in practice?
Sure. Let's say NEL has learned that birds can fly and that sparrows are birds. Using simple logic, it can then infer that sparrows can fly, even if it's never explicitly seen that statement before.
So it's like NEL is connecting the dots, using its existing knowledge to fill in the gaps and reach new conclusions.
Precisely. And NEL's reasoning capabilities, they go beyond simple deductive logic. It can also use probabilistic reasoning, taking into account the likelihood of different outcomes based on the information it has.
So it's not just dealing in absolutes, it's considering probabilities and making educated guesses about the world.
Exactly. And this ability to reason probabilistically, it's essential for dealing with the uncertainty and the ambiguity inherent in human language.
It's like NEL is learning to think more like a human, considering different possibilities, weighing the evidence before reaching a conclusion.
And this is where NEL's that never-ending learning process really becomes powerful. The more it reads, the more connections it makes, and the more sophisticated its reasoning abilities become.
It's like NEL is on a never-ending quest for knowledge, constantly expanding its understanding of the world and refining its ability to reason about it.
And unlike rule-based systems like AML, which are limited by the knowledge that's explicitly programmed into them, NEL has the potential to continue learning and evolving indefinitely.
It's a fascinating and somewhat daunting thought. But with all this knowledge and reasoning power at its disposal, what can NEL actually do? What are the practical applications of this technology?
That's a great question, and it's one that researchers are actively exploring. One of the most promising applications of NEL is in the field of knowledge discovery. Just imagine being able to query NEL about any topic and have it instantly provide a comprehensive overview of what it knows, complete with relevant facts, relationships, and even inferences.
It would be like having the world's most intelligent research assistant at your fingertips.
Exactly. And NEL's ability to connect those seemingly disparate pieces of information could lead to new insights and discoveries that humans might never have made on their own.
It's like NEL is helping us to see the world in new ways, revealing hidden connections and patterns that were previously obscured.
And beyond knowledge discovery, NEL's reasoning capabilities could also be applied to tasks like question answering, or text summarization, or even machine translation. Imagine a system that can not only translate languages, but also understand those nuances of meaning and context, providing truly accurate and natural-sounding translations.
Like, we're moving closer to a future where language barriers are no longer an obstacle to communication and understanding.
Precisely. And as NEL continues to learn and evolve, the potential applications of its technology they're only going to expand.
It's truly remarkable to think about how far we've come in the field of NLP, from those early rule-based chatbots to systems like NEL that are capable of learning and reasoning on a massive scale.
And both AL and LL have played crucial roles in this journey, demonstrating the different ways that we can build machines that understand and interact with human language.
A testament to the ingenuity and creativity of AI researchers who continue to push the boundaries of what's possible.
But let's delve a bit deeper into some of the challenges that NEL faces. In its quest for never-ending knowledge, one of the biggest hurdles is dealing with the inherent messiness and ambiguity of the internet. It's like it's trying to learn a new language from a dictionary that's constantly being updated, with slang, regional dialects, even misinformation. So how does NELL filter out all that noise? How does it extract reliable knowledge from such a chaotic source?
Yeah, that's a huge challenge. It's like trying to find a needle in a haystack. How does NELL make sure that it's not learning the wrong things?
Right, and that's one of the biggest challenges in NEL's design. It has to be incredibly discerning, constantly evaluating the credibility of its sources and the reliability of that. of the information it extracts.
So it's not just blindly absorbing everything it reads. It's like a fact checker, scrutinizing every piece of information before adding it to its knowledge base.
Exactly. NEL uses a variety of techniques to assess the trustworthiness of its sources. It looks for corroborating evidence from multiple websites. It analyzes the language used. It even considers the reputation of the website itself.
So NEL is learning to be like a critical thinker, evaluating information and forming its own judgments about what's believable and what's not.
And that critical thinking ability is so crucial, especially in today's world, where misinformation and disinformation are rampant online.
Yeah. We're all bombarded with so much information these days. It's more important than ever to be able to discern fact from fiction.
And NEL's ability to do just that makes it such a valuable tool for navigating the complexities of the digital age. It's like having a personal AI librarian who can help you sift through mountains of information and find those nuggets of truth.
That's a powerful image. But even with all these safeguards in place, I imagine that NEL must still encounter some challenges in its quest for never-ending knowledge. What are some of the other hurdles it faces?
One of the biggest challenges is the inherent ambiguity of human language. Words can have multiple meanings, and the same phrase can be interpreted in different ways, depending on the context.
It's trying to understand a joke. That relies on wordplay or cultural references. If you don't have the background knowledge, you'll miss the punchline.
Exactly. And NEL has to constantly grapple with those nuances of language, trying to disambiguate words and phrases and understand the intended meaning behind them.
So it's like NEL is learning to be a master of semantics, deciphering the subtle shades of meaning that we humans take for granted.
And that's no easy feat, but NEL's ability to learn from its mistakes and constantly refine its understanding of language, that's what makes it such a promising technology.
It's like NEL is on a never-ending quest to master human language, constantly pushing the boundaries of its understanding and becoming more sophisticated over time.
And as NEL continues to learn and evolve, it's helping us to understand the complexities of language in new ways, revealing hidden patterns and connections that we might never have noticed on our own.
It's like NEL is holding up a mirror to human language, showing us how we think and communicate in ways we never fully appreciated before.
And that's just one of the many reasons why NEL is such a fascinating and important project. It's not just about building a better machine. It's about expanding our own understanding of what it means to be human.
Well said. So we've got NEL, the rule-based pioneer that laid the foundation for chatbot technology, and NELL, the tireless student that's constantly learning and evolving, pushing those boundaries of machine intelligence. Two very different approaches, but both incredibly impactful in the field of NLP.
And both offer valuable lessons about the different ways that we can build machines that understand and interact with the world around them. All right, we've got this stack of notes here on machine learning. NLP, intent detection, word-to-vec, BERT, even glove. You've really been digging deep into this stuff. It seems like you want to get under the hood and figure out not just how these systems work, but like, why are certain techniques used and how can we tweak them to make them even better, right?
Yeah, and it's interesting how you've even included research that looks at the limitations of those classic approaches and how those newer techniques are reshaping the NLP landscape.
Like, one thing that really stood out to me was the evolution of word embeddings. Before 2013, it was all about one-hot encoding and TF-IDF. But those methods just couldn't really capture the nuances of language.
Exactly. With one-hot encoding, like king and queen would be seen as completely unrelated.
Yeah, no connection at all.
Total opposites almost. And that's where word-to-vec came in and really changed everything. So instead of treating words like isolated units, it uses a shallow neural network, which makes it super fast, to learn these dense vector representations, these word embeddings. And the cool thing is, these embeddings actually capture semantic relationships. Words used in similar contexts, they end up with vectors that are closer together in this abstract meaning space.
So instead of just saying king and queen are different, word-to-vec gets that they're related in a specific way, right? I'm guessing that's why it's so huge for NLP.
Absolutely. It's like teaching a computer to understand words not just as labels, but as concepts that exist in relation to other concepts. And word-to-vec does this using two main architectures, CBOW and skipogram.
And in the notes here, you really want to get into the nuts and bolts of how those work.
Yeah.
Let's start with skipgram. Like, how does that one work?
Okay, so imagine you have a sentence like, the quick brown fox jumps over the lazy dog. With skipgram, we take a center word, let's say fox, and try to predict the surrounding words like quick, brown, jumps over. And the goal is for the model to learn how to map words to these vectors so that words that appear in similar contexts, they have similar vectors.
So skipgram is all about figuring out what words tend to hang out together. But what are the actual steps involved in doing that? What happens inside the model?
So first, the model represents the input word, like in this case, fox, as a one-hot encoded vector. And then this vector is fed into a hidden layer, which acts like a projection layer, performing a simple linear transformation without any fancy activation function. The output of this layer is the word embedding for fox.
Got it. So the hidden layer is where that magic vector is created. What happens next?
Then, that embedding goes to the output layer, which uses a softmax function to predict the probability of each word in the vocabulary being a context word for fox. Words like jumps and over, they would likely have higher probabilities compared to a word like apple.
But I'm just thinking, calculating all those probabilities in the output layer, especially with a huge vocabulary, that seems like it would take forever.
That's a great point. That's a major challenge with this approach. And that's where techniques like negative sampling and hierarchical softmax come in. Negative sampling, for instance, it cleverly uses just a small sample of negative examples, words that are unlikely to be context words, instead of crunching through the entire vocabulary.
So it's like taking a smart shortcut that doesn't really sacrifice accuracy. These techniques basically make it possible to use these powerful word embeddings even when you're dealing with massive vocabularies, which opens up a whole world of possibilities, right?
Exactly. Now, CBOW works a bit differently. While skipogram predicts the context given a word, CBOW does the opposite. It predicts the center word given its context. Using our example again, if your context words were the and dog, CBOW would try to predict lazy.
So CBOW is like filling in the blank.
Yep.
While skipgram is more like expanding on a word. So what are the strengths and weaknesses of each approach? When would you choose one over the other?
So skipgram is really good at capturing those rarer words and representing their meaning because it focuses on those individual word relationships. But it does take longer to train because it's predicting multiple context words for each center word. CBOW, on the other hand, it's faster to train because it's only predicting one word at a time. And it tends to do well with common words. But it can struggle a bit with those rare words because their representations get averaged out when you consider all the context words.
So there's a trade-off between capturing the subtle meanings of rare words and training speed, which brings us to GloVe, which takes a more global perspective on these word embeddings, right?
That's right. Word2Vec, with both CBOW and skipgram, it focuses on those local co-occurrences within a specific window of words. GloVe, which stands for Global Vectors for Word Representation, it steps back and looks at the bigger picture. It builds a word co-occurrence matrix from the entire corpus, basically tracking how often words appear together overall.
So instead of just looking at the immediate neighbors, it considers like the entire social network of words.
Yeah, that's a great way to put it. And because GloVe uses this global information, it's really good at capturing those overall semantic relationships between words. It also creates these pre-computed embeddings, which can be super efficient for static models. But there's a trade-off. GloVe isn't as dynamic as Word2Vec. It doesn't adapt as easily to new words or changes in how words are used.
That makes sense. So if you're working with a fixed vocabulary and you need a solid pre-computed set of embeddings, GloVe seems like a good choice. But in a fast-changing environment like social media, Word2Vec's adaptability would be more valuable.
Precisely.
Yeah.
It all comes down to choosing the right tool for the specific task at hand.
Now, you've also included some research on BERT, this powerful model based on the transformer architecture and how it compares to these earlier methods. What makes BERT so special?
BERT, which stands for Bidirectional Encoder Representations from Transformers, it represents a major leap forward. Unlike Word2Vec and GloVe, which generate static word embeddings like a dictionary definition, BERT creates dynamic embeddings. So the representation of a word actually changes depending on its context.
So BERT takes into account the company a word keeps, so to speak. That seems like a huge advantage for truly understanding language.
Absolutely. This context awareness allows BERT to handle polysemy much better. So for instance, take the word bank. It could refer to a financial institution or the edge of a river. BERT would generate different embeddings for bank based on the surrounding words. While Word2Vec would just have one static embedding that tries to average those meanings.
So BERT has a much deeper understanding of how words actually function in language. What other key differences set it apart from Word2Vec?
BERT, being a deep transformer model, is far more complex than the shallow neural network structure of Word2Vec. And this means that BERT can capture those long-range dependencies in text, understanding the relationships between words, even if they're far apart in a sentence.
So it's not just about understanding individual words, but it's also about how those words relate to each other within a larger context?
Exactly. Even the way BERT is pre-trained is different. It uses a masked language modeling objective. So essentially, it's trained to predict masked words in a sentence, which forces it to develop this deep understanding of language structure and semantics.
It's like it's solving a giant crossword puzzle.
Yes. And another key difference is bidirectionality. Word2Vec usually learns from text in one direction, either left to right or right to left. BERT, however, reads the entire sentence simultaneously, capturing that bidirectional context.
So BERT just seems to outperform Word2Vec in almost every aspect. But there has to be a trade-off somewhere, right? Nothing's perfect.
Yeah, you're right. There is. The major trade-off is computational cost. BERT requires a lot more computational power, both for pre-training and when using it for tasks. Word2Vec, with its simpler architecture, is much faster and lighter.
So BERT is like the high-performance sports car, while Word2Vec is like a nimble scooter.
Exactly.
So BERT is the go-to choice when you need that high level of accuracy, but Word2Vec might be more practical when speed and efficiency are the priority.
Exactly. And there are still plenty of situations where Word2Vec shines. For instance, if you need fast, lightweight embeddings for tasks like topic modeling or basic clustering where the context doesn't play a huge role, Word2Vec could be the better choice. It's all about choosing the right tool for the job.
Speaking of choosing the right tool, how do we even know if the word embeddings we create are any good? How do we measure their quality?
That's a great question. Evaluating word embeddings is a crucial step in any NLP project. One common approach is what we call intrinsic evaluation, which involves tasks that directly assess the properties of the embeddings themselves.
So instead of looking at how well the embeddings perform on a real-world task, we're examining their inherent qualities, like judging a cake by its appearance before tasting it.
That's a good analogy. For example, we could use cosine similarity to measure how similar the embeddings for two words are. If the embeddings capture semantic meaning well, words like king and queen should have a high cosine similarity.
So if the embeddings understand meaning, then words with similar meaning should have similar representations. Are there other methods for this intrinsic evaluation?
Another popular one is analogy testing, like the classic king, man plus woman, queen. If the embeddings have grasped those relationships between words, they should be able to solve these kinds of analogies.
I can see how that would be a good indicator, but I imagine there are times when these intrinsic methods aren't enough. What about evaluating how these embeddings actually perform in a real-world task?
Yeah, you're right. Sometimes you need to see how well they do in practice. That's called extrinsic evaluation. So you'd use the embeddings as input features for tasks like sentiment analysis, named entity recognition, or even machine translation.
So you're seeing how those embeddings contribute to the overall success of a larger NLP system, like finally getting to taste that cake.
Exactly. Better embeddings should result in better performance on these downstream tasks. And there are even more specialized methods like probing tasks, which are designed to test what specific types of linguistic information are captured by those embeddings. For example, you could have a syntactic probe that checks if the embeddings encode part of speech information. It's like giving the embeddings a pop quiz.
So there's so much depth to these word embeddings. It's amazing how much information they can pack into those vectors. But even with all these advancements, they aren't perfect, are they? You mentioned some potential issues like the problem of polysemy.
Right. Polysemy, as we mentioned earlier, is when words have multiple meanings. And Word2Vec and Glove, with their static embeddings, they can really struggle with this. But BERT, with its context-aware approach, it's much better equipped to handle those nuances.
So BERT is like the multilingual friend who can effortlessly switch between languages and understand those different meanings based on the context.
Yes.
Are there other challenges we need to be aware of?
Definitely. Another big one is the curse of dimensionality. So word embeddings can often be very high dimensional, which can lead to increased memory usage and slower processing times. Thankfully, we have dimensionality reduction techniques like PCA or UMAP that can help us create smaller, more manageable representations while still preserving most of the crucial information.
So it's this constant push and pull between wanting those rich, expressive embeddings and needing to keep things manageable and efficient.
Absolutely. Finding that balance is a key challenge in NLP, especially as we develop more sophisticated models that rely heavily on these representations.
Now, shifting gears a bit, it looks like you're also very interested in intent detection.
Yeah, it's such a crucial aspect of natural language understanding, especially in today's world.
Could you explain what intent detection is and why it's so important, especially for those of us who might not be familiar with the technical jargon?
So imagine you're chatting with a virtual assistant or a chatbot. You ask it a question or give it a command. Intent detection is what allows that system to figure out what you actually mean, what your goal is behind those words. It goes beyond just understanding the words themselves. It's about deciphering the intention behind those words.
So it's not just about what you say, but about what you mean to do. Like understanding the difference between I'm hungry and can you please make me a sandwich?
That's a perfect example. So in the first case, you're simply stating a fact, while in the second case, you're making a request. Intent detection helps these systems understand that difference so they can respond appropriately.
This seems incredibly valuable for all those chatbots and virtual assistants we're interacting with more and more these days.
Right.
They need to understand what we actually want them to do, not just the literal words we use.
Exactly. Intent detection is key in making those systems feel more intelligent and helpful.
So how do we actually build an intent detection system? What are the steps involved in teaching a computer to read between the lines?
It usually involves a pipeline with several stages. First, we need to gather the data, which could be anything from customer support queries to chat logs to emails, basically any text where we want our system to be able to recognize the intent behind it.
So it starts with collecting all the conversations and messages that we want our system to learn from.
Exactly. Once we have that data, we move on to text preprocessing. This is all about cleaning and normalizing the text. We might convert all the text to lowercase, remove punctuation, and eliminate those common words like the, is, and that don't carry much meaning. These are called stop words. These steps help to standardize the text and reduce noise.
So it's like removing all the unnecessary clutter and making the text easier for the system to digest.
Precisely. And once we have this clean text, we move on to feature extraction. This is where we transform those pre-processed words into numerical representations that our machine learning models can actually work with.
So we're converting words into numbers, translating them into a language that computers can understand.
Yes, that's a great way to think about it. In the past, techniques like bag of words and TF-IDF were commonly used. These methods basically count word occurrences or weigh words based on their importance. But now we have more sophisticated approaches like word embeddings and those transformer embeddings that we talked about earlier.
So we could actually use techniques like word2vec or even BERT to generate embeddings as features for intent detection.
Absolutely. Using those embeddings that encode semantic meaning can significantly improve the accuracy of our intent classification. Once we have these numerical features, we move on to model inference, which is where the actual magic happens. This is where we use a machine learning model to predict the intent behind a given text.
So we've gone from gathering this messy text to creating these sophisticated numerical representations that our model can use. What kind of models are typically used for this intent detection task?
So in the past, traditional machine learning models like logistic regression, random forests, or support vector machines were often used, and they can work well for simpler tasks, but they don't handle long-range dependencies in text very effectively.
You need a model that can remember what happened earlier in the sentence or even in the previous sentences.
Exactly. That's why deep learning models like LSTMs, CNNs, and those powerful transformers, particularly BERT-based models, have become the standard for intent detection. They can capture those complex relationships in text and make much more accurate predictions about the underlying intent.
It sounds like BERT is a real all-star in the NLP world, excelling at both understanding language and figuring out what we humans are actually trying to do with our words.
Yeah, it really is a remarkable model, but there's still one crucial step we haven't talked about: post-processing. This is where we apply some business logic and refine those model predictions.
Post-processing, what kind of adjustments or refinements do we typically make at this stage?
One common technique is confidence thresholding. So if the model's only slightly sure about its prediction, we might want to flag it for human review.
It's always good to have that human backup, especially when dealing with something as nuanced as intent.
Absolutely. Another aspect is handling multiple intents. So what happens when a user expresses more than one goal in their message? We might need to use special techniques to identify and address all of those intents.
So it's like recognizing that someone might be asking a question and making a request at the same time.
Precisely. And sometimes we might use fuzzy matching or even rule-based overrides to catch those tricky cases that the model might miss.
It sounds post-processing is all about adding an extra layer of intelligence and robustness to the system. But even with all these sophisticated techniques, how do we know if our intent detection system is actually working well?
That's a crucial question. Evaluating the performance of an intent detection system is absolutely essential. We can use standard classification metrics like accuracy, precision, recall, and the F1 score.
Those sound familiar. We talked about those when discussing word embeddings, right?
Exactly. Those same metrics can be applied here to see how well our model is doing at predicting the right intent. We can also use a confusion matrix, which is a helpful tool to visualize how well the model is distinguishing between different intents.
So it's like a scorecard that shows us where the model is excelling and where it might be making some mistakes.
Yes, it's a very useful way to understand the model's strengths and weaknesses. But we can go even further and use metrics that are specific to the NLP, like semantic similarity. This measures how well the model is understanding the meaning of different intents, not just matching words.
So it's not just about getting the right label, it's about truly understanding the subtle differences between different intents.
Exactly. And in many cases, the most valuable feedback comes from humans. We need real users to test the system and tell us where it's making mistakes.
Yeah.
That human-in-the-loop evaluation is essential for continuous improvement.
It's about combining those objective metrics with the subjective experience of real users.
I like that analogy. Ultimately, it's all about building a system that's both accurate and useful in the real world.
So we've built our amazing intent detection system. It's performing well in our tests, but now we need to release it into the wild. What are the challenges of deploying these systems in the real world, and how do we make sure they can handle all the complexities of real-world interactions?
So we left off talking about how to actually deploy these complex NLP systems in the real world. And it seems like there's a huge leap from those neat and tidy research environments to actually handling the messiness of real-world data and user interactions.
Yeah, deployment definitely brings a whole new set of challenges.
What are some of the biggest hurdles you encounter when moving from theory to practice? I'd say one of the most common issues is data mismatch. And this happens when the data we use to train the model doesn't quite reflect the data it encounters in the real world.
So it's like training a self-driving car in a perfectly simulated world and then letting it loose on the streets of a bustling city.
Exactly. The model hasn't been prepared for that kind of linguistic chaos.
Yeah.
Another challenge is concept drift.
Concept drift. That sounds almost philosophical.
It is. It happens when the relationships between the input features and the output we're trying to predict change over time. Think of like fraud detection. The methods scammers use are constantly evolving. So a model trained on historical data might miss those new tricks.
So the model's knowledge can become outdated.
Precisely. And this can happen gradually or suddenly, making it really tough to maintain accuracy over time. We also need to be wary of something called label leakage.
Label leakage. That sounds dangerous.
It can be just as harmful to our models. It happens when information from the target variable, the thing we're trying to predict, accidentally sneaks into the training data.
So during training, the model looks like a rock star, but in the real world, it falls flat.
Exactly. We need to be very careful about how we prepare our data to avoid this kind of leakage.
Now, what about the practical aspects of performance? I imagine speed is critical in many applications.
Absolutely. Latency, which is the time it takes for a model to process a request, is crucial in real-time applications like chatbots. A model might be accurate, but if it takes too long to respond, it's going to create a frustrating user experience.
Nobody wants to wait 5 minutes for a chatbot to come up with a response.
Exactly. We need to consider techniques like model compression or even specialized hardware to make sure these systems are fast and responsive enough for real-world use.
So deploying these ML models in the real world is all about balancing those competing demands of accuracy, speed, robustness, and handling all those unexpected curveballs that reality throws our way.
It's a constant dance for sure.
Now, let's talk about some of those cutting-edge techniques you've been researching. You've mentioned catastrophic forgetting, which sounds a bit ominous. Can you tell us more about that?
It definitely has a dramatic name. Catastrophic forgetting happens when a neural network, after learning to perform a new task, loses its ability to perform well on those earlier tasks it was trained on.
That sounds like a major problem, especially for systems that need to learn and adapt continuously.
In the context of fine-tuning, which is where we take a pre-trained model and adapt it to a new task, catastrophic forgetting can occur because we're essentially retraining the entire model on a new data set. This allows it to learn the new stuff, but it can overwrite the knowledge it had acquired before.
So it's like trying to cram too much information into a small box.
Exactly. And this phenomenon is related to what we call the stability-plasticity dilemma. Neural networks need to be plastic, able to learn new information, but also stable enough to retain those previously learned skills. Catastrophic forgetting happens when the plasticity kind of outstrips the stability.
Are there ways to prevent this forgetting from happening?
Yeah, researchers are actively working on various solutions. One approach is regularization. It's a technique where we add a penalty to the loss function that discourages the model from making drastic changes to the weights that were important for those old tasks.
So we're constraining its ability to change too dramatically to protect that previous knowledge. What other techniques are there?
Another promising approach is based on replay, essentially storing examples from those old tasks and periodically showing them to the model during training on the new task.
It's like giving the model refresher courses.
Yes, exactly. And a third approach is to use adapters or parameter-efficient fine-tuning techniques, LaRA. Instead of retraining the entire model, we freeze most of the weights and only train a small set of additional parameters.
So these methods are all about finding ways to learn new things without sacrificing the knowledge we've already gained.
That's a great way to put it. And the field is constantly advancing, and these techniques are becoming more sophisticated all the time.
You mentioned earlier that fine-tuning was a major step forward in NLP. Are there any other breakthroughs in this area that you're particularly excited about?
Yeah, one of the early breakthroughs was ULMFT, which stands for Universal Language Model Fine-Tuning. It introduced several innovative techniques like discriminative fine-tuning, slanted triangular learning rates, and gradual unfreezing.
Those sound intriguing. Can you break those down for us?
So think of discriminative fine-tuning as treating different parts of the model differently. The lower layers, which learn more general knowledge about language, are trained at a slower pace. And the upper layers, which are more task-specific, are trained more aggressively.
So it's about tailoring the training to the specific needs of each layer.
Exactly.
What about slanted triangular learning rates?
That's all about managing the learning rate, which controls how quickly the model adjusts its weights during training. With slanted triangular learning rates, the learning rate starts low, gradually increases to a peak, and then gradually decreases again.
It seems like a way to find that sweet spot between making progress quickly and making sure the model doesn't overshoot the target. And what about gradual unfreezing?
Gradual unfreezing is about controlling which parts of the model are allowed to learn at each stage of training. We start by training only the last layer, then unfreeze the second to last layer, and so on.
So ULMFT was like a pioneer in the world of fine-tuning, setting the stage for many of the techniques we use today.
Absolutely. It was a major leap forward, demonstrating the power of taking those pre-trained models and adapting them to specific tasks. And since ULMFT, we've seen even more powerful techniques emerge, like model merging and distillation.
Model merging sounds like something out of science fiction, combining the intelligence of multiple models into one super intelligent entity.
It's a fascinating area of research. Model merging involves combining multiple pre-trained models into a single, more powerful model. We can average the weights of different models or use more sophisticated techniques that consider the relationships between those models.
So instead of training a model from scratch, we're essentially pooling the collective wisdom of several experts.
That's a great analogy. And model distillation is a technique where we train a smaller model, called the student, to mimic the behavior of a larger, more complex model called the teacher.
It's like an apprentice learning from a master craftsman.
Exactly. The student model is typically much faster and more efficient to run while still retaining much of the knowledge of that larger model. It's a powerful technique for making those large resource-intensive models more practical for real-world applications.
Are there any specific examples of model merging or distillation that have really impressed you?
One recent paper that caught my eye was about A.R.C.E, a framework for model merging and multi-teacher distillation. It's designed to combine and compress knowledge from those massive language models we've all heard about creating smaller, more specialized models that still perform remarkably well.
So they're taking the best parts of several large language models and distilling them into a more compact and efficient model.
That's a great way to visualize it. RC has shown a lot of promise in tasks like medical question answering and text generation, highlighting the potential of these advanced techniques to make powerful NLP more accessible.
That's really exciting. It seems like we're constantly pushing the boundaries of what's possible with language models. You've also mentioned model stock, which seems to be another intriguing approach to model merging.
Yes, model stock is a really interesting technique that builds upon the idea of simple model averaging. Instead of just averaging the weights of multiple models evenly, model stock strategically minimizes the distance from the weight center in a high-dimensional space.
So it sounds like we're being more strategic and deliberate about how we combine these models.
That's a great analogy. Model stock takes inspiration from geometry and optimization to find a better way to merge models, leading to improved generalization and more stable performance.
It's fascinating how these techniques draw inspiration from other fields, finding creative solutions to complex problems. Now, let's dive into another key architecture in NLP, the Encoder-Decoder framework. Can you give us a high-level overview of how it works and why it's so widely used?
The encoder-decoder architecture is a fundamental framework for tasks that involve mapping one sequence to another. Think of machine translation, where you're taking a sentence in one language and converting it into another language, or text summarization, where you're condensing a long piece of text into a shorter version.
So it's all about transforming one sequence of information into a different sequence while preserving the essential meaning.
Exactly. The encoder-decoder framework consists of two main components, just as the name suggests, an encoder and a decoder. The encoder takes the input sequence, like a sentence in English, and processes it to create a fixed-length representation, often called a context vector.
Yeah.
And this vector captures the essence of the input sequence.
So the encoder is like a chef who takes a bunch of raw ingredients and blends them together to create a concentrated flavor base.
I like that analogy. And then the decoder takes that concentrated essence, that context vector, and uses it to generate the output sequence, the translation into French, the summary of the text, or whatever the desired output is.
So the decoder is like the baker who takes that concentrated flavor base and uses it to create a delicious and beautifully formed pastry?
Exactly. And what makes this architecture so powerful is its ability to handle variable length sequences. The input and output don't have to be the same length, which is essential for tasks like translation or summarization.
Now, you've also mentioned something called token generation parameters, which seem to be related to the decoder. What are those and why are they important?
Token generation parameters control how the decoder generates the output sequence word by word or token by token. One of these parameters is temperature, which controls the randomness of the generation process.
A higher temperature would lead to more creative and unpredictable output, while a lower temperature would result in more deterministic and predictable output.
That's a good analogy. We also have parameters like top K and top sampling, which limit the decoder's choices to a subset of the most likely tokens.
These parameters seem like powerful tools for fine-tuning the creative process, balancing that tension between generating something novel and making sure it's still coherent and relevant.
Exactly. They give us a lot of control over the generation process, allowing us to adapt it to different tasks and preferences.
Now, you mentioned earlier that deep neural networks can be prone to the vanishing gradient problem. You've also hinted at a solution called residual layers or skip connections. Can you explain how those work and why they're so important?
Yeah, so the vanishing gradient problem is a major challenge when training deep neural networks. As the gradients, those signals that tell the model how to adjust its weights, propagate back through the layers, they can become increasingly small, especially in those earlier layers.
So those early layers might not get the memo about how to improve, leading to slower learning.
Exactly. Residual layers, also known as skip connections, address this problem by adding shortcuts that bypass one or more layers. This allows those gradients to take a more direct route, preventing them from fading away before they reach those crucial early layers.
It's like adding express lanes to a busy highway.
Yes, that's a great way to put it. These shortcut connections help to maintain information flow throughout the network, enabling it to learn more effectively, even with a large number of layers.
Are there any other benefits to using residual layers?
Besides addressing the vanishing gradient problem, they also encourage something called identity mapping. So if a layer doesn't learn anything useful, it can simply pass the input through unchanged. This makes it easier for the network to learn complex functions, as it doesn't have to start from scratch with every layer.
It's about working smarter, not harder.
Exactly. Residual layers have revolutionized deep learning, leading to the development of much deeper and more powerful models.
Now, you've also included some notes on LSTMs, which seem to be another type of recurrent neural network, like those RNNs we talked about earlier. How do they differ from standard RNNs, and why are they so important?
LSTMs, or long short-term memory networks, are a specialized type of RNN specifically designed to address the vanishing gradient problem. They achieve this by introducing a memory cell and a set of gates that they control the flow of information through the network.
It's like adding a memory bank to the network, allowing it to remember important information over longer sequences.
Exactly. Standard RNNs have a very short memory, making it difficult for them to capture those long-range dependencies. LSTMs, with their memory cells and gates, can overcome this limitation, making them incredibly effective for tasks where that long-term context is crucial.
What are some of the real-world applications where LSTMs shine?
They've been remarkably successful in areas like speech recognition, where understanding the entire sequence of spoken words is essential, machine translation, where capturing the context of entire sentences and paragraphs is crucial, in time series forecasting, where recognizing those patterns that stretch across time is key.
So LSTMs are like those multi-talented individuals who excel in various domains. Now, shifting gears a bit, let's delve into some statistical concepts that seem to be relevant to your research. You've mentioned the p-value in the context of linear regression.
Yeah.
Can you explain what the p-value is and why it's important, especially for those of us who might be a bit rusty on our statistics?
The p-value is a fundamental concept in hypothesis testing, the process of using data to determine whether a specific claim or hypothesis is likely to be true. In the world of linear regression, which is a technique for modeling the relationship between variables, the p-value is used to assess the statistical significance of those relationships.
It tells us whether the relationship we're seeing between variables is likely to be real or just due to random chance.
Exactly. The p-value represents the probability of observing the data we've collected if there were actually no real relationship between those variables.
It's like saying, if this relationship were purely coincidental, how likely is it that we would have observed these specific patterns in the data?
That's a great way to think about it. And if the p-value is very low, typically below 0.05, it suggests that it's unlikely we observed those results by chance alone.
So it's like a measure of how surprising the results are. The lower the p-value, the more surprised we are.
Exactly. It's an important tool for separating those statistically significant relationships from those that might be just random noise.
Now, you've also mentioned PCA, or principal component analysis, which seems to be a technique for taming those high-dimensional data sets that we often encounter in machine learning. Can you demystify PCA for us?
PCA is a powerful technique for reducing the dimensionality of data while preserving as much of that important information, that variability, as possible. It does this by finding a new set of variables called principal components, which are basically linear combinations of the original variable.
It's like taking a complex multi-layered cake and finding a way to represent its flavors and textures using a few key ingredients.
I love that analogy. And these principal components are ordered by how much variability they explain. The first principal component captures the most variability, the second captures the second most, and so on. By keeping just those first few principal components, we can significantly reduce the dimensionality of the data while still retaining most of the important information.
So it's like creating a more compact and manageable version of the data without losing its essential flavor. What are some of the benefits of using PCA?
It's a very versatile technique that can be used to reduce noise in the data, making it easier for our models to learn the true patterns, to visualize the data in a lower dimensional space, making it easier for us humans to understand those patterns, and even to speed up the training of machine learning algorithms, making the whole process more efficient.
It sounds like a real workhorse in the world of data analysis.
It certainly is. It's a valuable tool for simplifying complex data sets without sacrificing too much valuable information. And I think you've hit on the key theme here. Many of the techniques we've discussed, from residual layers to LSTMs to PCA, are all about addressing those challenges of working with those large, complex, and often messy data sets that we encounter in the real world.
It's like we're constantly coming up with new tools and strategies to tame the wild beast of data, finding ways to make it more more manageable, more understandable, and ultimately more useful.
Exactly. It's an exciting time to be working in this field as we continue to push the boundaries of what's possible with these powerful techniques.
This has been a fantastic journey through the world of machine learning. We've covered everything from those fundamental building blocks of language word embeddings to the complexities of understanding intent, the challenges of deploying these systems in the real world, and some of the most advanced techniques for fine-tuning, merging, and optimizing these powerful models.
I agree. It's been a great conversation, and it highlights how much progress has been made in this field and how much more is yet to come.
I'm already eager to hear what's next. I think we need to pause here for another break. When we come back, let's explore some of those real-world challenges in more detail, delve into evaluating those fascinating RJ systems, and discuss how we can combine different approaches, like using XGBoost for text classification.
Sounds great. I'm looking forward to continuing our exploration.
All right, so we're back for the final part of our deep dive into this world of machine learning. It's been quite a journey so far.
It really has. We've explored so many fascinating concepts, from the fundamentals of word embeddings to those cutting-edge techniques like model merging and distillation.
Yeah, and I'm particularly eager to discuss those real-world challenges that we touched on earlier. We've all heard those stories about AI systems making bizarre mistakes or behaving in unexpected ways. What are some of the biggest gotchas we need to watch out for when we actually deploy these models in the wild?
One of the classic pitfalls is what we call data mismatch. And this happens when the data that we use to train our models doesn't quite accurately reflect the real-world data that they encounter in production.
It's like training a self-driving car in a perfectly simulated world with no unexpected pedestrians or crazy weather, and then letting it loose on the streets of a bustling city.
Exactly.
Yeah.
The model hasn't been prepared for that kind of linguistic chaos. Another challenge is concept drift.
Concept drift? That sounds almost philosophical.
It is. It happens when the relationships between the input features and the output that we're trying to predict change over time. Think of fraud detection. The methods that scammers use are constantly evolving. So a model trained on historical data might miss those new tricks.
So the model's knowledge can become outdated.
Precisely. And this can happen gradually or suddenly, making it really tough to maintain accuracy over time.
Mm-hmm.
We also need to be wary of something called label leakage.
Label leakage. That sounds almost like a medical condition?
It can be. It can be just as harmful to our models.
Yeah.
It happens when information from the target variable, the thing we're trying to predict, accidentally sneaks into the training data.
So the model might appear to be performing really well during training, but it's essentially learned to cheat, and its performance in the real world will be disappointing.
Precisely. We need to be very careful about how we prepare our data to avoid this kind of leakage.
Now, besides these data-related challenges, I imagine there are also practical considerations when deploying these models. Speed and efficiency seem particularly crucial in today's fast-paced world.
Absolutely. Latency, which is the time it takes for a model to process a request, is a major concern in many real-time applications. A model might be super accurate, but if it takes forever to respond, it's going to create a terrible user experience.
I think we've all experienced those frustrating moments when technology just doesn't keep up with our expectations.
Exactly. And it's not just about user experience. In some applications like high-frequency trading or real-time fraud detection, even milliseconds can make a huge difference. So we need to be very mindful of those performance considerations when we design and deploy our models. We might need to explore techniques like model compression, which is about creating smaller, more efficient versions of our models. Or even consider using specialized hardware that's optimized for these kinds of tasks.
It's fascinating how all these different aspects, the quality of the data, the design of the model, and those practical considerations of performance all come together to determine the success of a machine learning system.
It's truly an interdisciplinary field that draws on insights from computer science, statistics, linguistics, and even psychology.
Now, I'd love to talk about those RAG systems or Retrieval-Augmented Generation systems that you've mentioned. They sound incredibly powerful, but also quite complex.
RGRA systems represent a really interesting evolution in how we build language models. Instead of relying solely on the knowledge that's been baked into the model during training, RGRA systems can access and retrieve information from external knowledge bases,
right,
like Wikipedia or a vast collection of documents.
So it's like having a super intelligent research assistant that can instantly pull up relevant information from a massive library.
That's a great analogy. And this ability to access external knowledge makes RA systems incredibly powerful for tasks like question answering, where you need to provide accurate and up-to-date information, or for building chatbots that can have more informed and engaging conversations.
But I imagine that evaluating these RJ systems presents unique challenges. It's not just about assessing the quality of the generated text anymore, but also about how well the system retrieves relevant information from that external knowledge base.
You're absolutely right. We need to consider both the retrieval aspect and the generation aspect when we're evaluating RG systems. On the retrieval side, we might use metrics like precision and recall to assess how well the system is finding those truly relevant documents or passages. And on the generation side, we can still use those familiar metrics like BLEU or OJ to assess the fluency and accuracy of the generated text.
So it's a two-pronged evaluation approach. But you've also hinted that those traditional metrics might not be enough to capture the full picture when it comes to RGRO systems.
That's true. We also need to consider faithfulness and context relevance. Is the generated text factually consistent with the information that was retrieved?
Mm-hmm.
Does it accurately reflect the context of the query and the retrieved documents? It's about making sure that the system isn't just stringing together words that sound good, but actually providing meaningful and reliable information.
It's almost like evaluating a research paper. You want to make sure that the arguments are well supported by the evidence and that the conclusions are justified.
That's a great comparison. And to address these more nuanced aspects of RE evaluation, researchers are developing new methods that go beyond those traditional metrics. These methods often incorporate human judgments or use sophisticated techniques to assess the alignment between the retrieved information and the generated text.
It's an exciting area of research, and I'm eager to see how these evaluation methods evolve as RA systems become more prevalent.
Me too. It's a testament to how quickly the field of NLP is advancing and how we're constantly pushing the boundaries of what's possible with language models.
You know, I was working with an LLM the other day, and it was kind of a funny situation.
Oh, yeah.
I was trying to get it to just give me some simple JSON, like a list of car features and makes and models.
Right.
And instead of giving me that nice, clean JSON, I got this like Shakespearean sonnet about, praising the chariot of steel.
Wow.
The rhyming was pretty impressive.
Yeah.
But definitely not what I was looking for.
Very helpful.
And it really highlights this whole challenge we have with LLMs, getting them to produce structured data that's actually reliable.
Yeah, it's like they've got this flair for the dramatic, but sometimes you just need them to stick to the script, Exactly. And that's where these structured outputs come in, making sure that they give us that JSON or XML or HTML,
right?
Something that our systems can actually work with.
Yeah, exactly. So it's less Shakespeare, more data analyst.
I like that. So think of those formats, the JSON, the XML, as those meta structures. Yeah, they're like the blueprints that make sure that data comes out nice and neat and tidy and ready to be used.
Okay, so blueprints. I like that analogy.
Yeah.
But for someone who's not a coder, why should they care about this? What difference does it make in the real world?
Well, let's say you've got a company and they're trying to analyze customer reviews to figure out how to improve their products.
Okay.
They could use an LLM to try to pull out the key feedback from thousands of reviews.
Right.
But if the output's just this jumbled mess of text, it's practically useless.
Yeah, it's what do you even do with that?
But if that LLM was trained to produce structured output,
okay.
You got a nice, neat little table with columns for product, feature, sentiment, specific feedback.
Yeah.
Now you've got something you can actually work with.
So it takes that wall of text and makes it actually organized and useful.
Exactly.
So it's not just about making data pretty, though, right?
Yeah.
There's more to it.
Oh, yeah, for sure. So structured output, it actually lets us peek into the LLM's thought process.
Oh, interesting.
Yeah, we can actually trace how it arrived at its conclusions, which is super valuable for debugging.
Okay, I see where you're going with this.
Let's say you have an LLM helping review legal documents, and it flags a contract clause as potentially problematic.
Okay.
Well, with structured output, you can actually see the reasoning chain that led it to that conclusion.
So it's showing your work, not just giving the final answer.
Exactly. It builds trust in the system.
And that makes the output more reliable as well.
For sure, because when we enforce that specific format,
Yeah.
we really reduce the chance of the LLM just hallucinating or making stuff up.
Because no one wants to be misled by an AI, especially if they're using it for important decisions.
Exactly. And it's not just about accuracy. It's about control.
Okay.
By setting the rules of the output format, you're essentially guiding the LLM's behavior.
So we're moving away from this idea of LLMs as these like black boxes, and we're getting more transparency and control.
Exactly. And there's some really clever techniques for enforcing these structures.
Okay, let's hear it.
We've got constrained decoding reinforcement learning, prompting self-refinement, and function calling.
Okay, that's a lot. So let's start with constrained decoding.
Okay.
What's the basic idea there?
Think of it like a bouncer at a club,
Okay.
only letting certain words or tokens into the output based on the grammar rules you set.
Yeah.
So if you want JSON output,
Yeah.
you define the rules of JSON, and the LLM can only produce text that fits that format.
So it's like setting up guardrails to keep the output in check.
Exactly. And it's great for guaranteeing you'll get a properly formatted output every time.
Sounds foolproof. Are there any downsides to being so strict with the LLM?
Well, sometimes being that strict can interfere with the LLM's natural flow and creativity.
Okay.
So the output might sound a bit robotic.
Mm-hmm.
But researchers are working on algorithms that find a balance between, control and fluency.
So it doesn't sound like it's reading from a textbook.
Exactly.
All right. What about reinforcement learning? How does that fit in here?
Reinforcement learning, or RL, is kind of like training a dog with treats.
Okay.
You reward the LLM when it produces a well-formatted output, and you penalize it for mistakes.
I see.
And eventually it learns to produce that desired structure pretty consistently.
So positive reinforcement for AI,
Exactly.
is there a specific type of RL that's used here?
One that's showing a lot of promise is called Guided Relative Policy Optimization, or GRPO.
GRPO.
It's known for its stability and efficiency, which is really important when we're dealing with these massive models.
Stability, yeah. We don't want the LLM to go haywire just because we gave it a virtual cookie.
Right. We want a reliable system, not a rogue AI.
So GRPO is like that patient dog trainer that gets results?
Yeah.
All right, what about prompting and self-refinement?
So this one's a bit more intuitive.
Okay.
You give the LLM clear instructions in the prompt, like output only valid JSON.
Right.
And they're usually pretty good at following those cues.
So you're just being upfront about what you want.
Yeah,
Like
exactly.
telling a friend, hey, I need a ride at 5 p.m. sharp.
Exactly. And then we add self-refinement to that.
Okay.
So the LLM actually checks its own work
Uh-huh.
and tries to fix any errors before giving you that final output.
It's like a built-in editor.
Exactly.
And then we've got function calling. Is that the last one?
That's the last one.
What's special about that?
So function calling is all about giving the LLM a specific job description with a very defined structure for the output.
Okay.
Think of it like ordering a pizza online.
Okay.
You've got those neat little boxes to pick your crust and your toppings and the size.
Right.
So the function is like that order form. It predefines the structure of your pizza, or in this case, the data output.
So less creative writing, more like filling in the blanks.
Precisely. It's great for things like generating JSON objects where you have clear fields and data types.
So we've got these 4 powerful tools to get LLMs to produce that structured data.
Yeah.
But I'm curious how companies like Google, with all their AI expertise, are tackling this challenge.
Oh, they are definitely at the forefront of this.
What are they doing?
They're focused on building these really intuitive tools that let developers easily enforce schemas.
Okay.
And they just relentlessly train their models to understand and follow those schemas.
So they're pushing the limits, but let's start with the developer tools. What are they doing there?
One of the coolest things they've done is with their newest AI model, Gemini.
Okay.
It has this feature called Structured Output Mode within their Vertex AI platform.
Uh-huh.
Imagine you need some data in a very specific JSON format.
Okay.
You just give Gemini the JSON schema, like the detailed blueprint of what you need.
Yeah.
And it will deliver exactly that. No funny business, no poetic detours.
So you order that custom data structure and Gemini's the master craftsman.
That's the perfect analogy.
Oh, delivers it.
And their documentation suggests it makes responses a lot more deterministic, meaning you can be confident you're getting what you asked for.
So it's like a guarantee that your data will always be perfectly formatted.
Yeah, you don't have to double check or clean up messy outputs.
It's got to save developers so much time.
Tons.
But how does Gemini actually do this? Is there like a magical JSON validator running behind the scenes?
Not magic, but pretty impressive engineering.
Okay.
They've invested heavily in fine-tuning their models to understand and follow these schema definitions.
Okay.
They've probably trained Gemini on these massive data sets with tons of different schemas.
I see.
So it's become really good at interpreting and adhering to those structural cues.
So they're training these models to be bilingual.
Exactly. Fluent in both human language and data structural language.
And this isn't just with Gemini, right?
Nope. They're applying these techniques to other models as well, like PaLM 2.
It's cool to see how Google's making these techniques accessible to developers.
Yeah.
But before we get into how we can measure how well LLMs are actually doing at this,
Yeah.
does Google ever use any of those older parsing techniques, or are they all in on training the models to do it?
Their focus is definitely on training the models to understand structure, like intrinsically. But, they're practical.
Yeah.
They might still use some traditional parsing in certain pipelines that need absolute precision.
Yeah.
But it seems like their vision is really for these models to handle this natively.
So it's a multi-layered approach. But now I'm really curious, how do we actually measure how well an LLM is doing at following these formatting rules? How can we be sure they're not just getting lucky sometimes?
That's where the fun of evaluation comes in.
All right.
Google, being Google, has actually been instrumental in creating a benchmark for this very purpose.
Okay.
It's called Instruction Following Evaluation, or AIML for short.
AIML. Yeah, I've heard of that. That's getting a lot of attention.
For good reason.
Yeah.
So AIML rigorously tests an LLM's ability to understand and execute instructions, and especially the ones related to formatting. It's not about subjective judgments, it's about verifiable results.
Okay.
AIML uses scripts to check if the LLM's output actually matches the instructions.
So it's like a really strict teacher checking every detail of your homework.
That's a great way to put it. And AIML does not go easy on these LLMs.
No.
It throws hundreds of prompts at them, each with specific instructions.
Oh, wow.
And a clear yes or no answer in terms of compliance.
So it's not just, can you produce JSON? It's how consistently can you do it?
Exactly, across all kinds of scenarios.
And what have the results shown?
They've been really revealing when GPT-4 was evaluated with AIML, it got an accuracy of around 83.6% in following the instructions, while PaulM2 Small scored 55.8%.
Okay.
And if you break it down by the type of instruction, GPT-4 was significantly better at the tasks related to formatting, like producing valid JSON.
So there's still room for improvement, even for the best.
Absolutely.
But having that benchmark like AIML is crucial for driving progress.
For sure, it helps researchers pinpoint areas where a model might be struggling,
Right.
like handling complex XML or sticking to specific punctuation rules.
Okay.
And then they can focus on improving those aspects.
Well, they do say what gets measured gets improved. But before we move on to some of the potential pitfalls and edge cases, is AIML the only game in town for evaluating this?
AIML is definitely the main benchmark for overall instruction following, including format fidelity.
Okay.
But there are some more specialized efforts emerging.
Like what?
So there's this one called JSON Schema Bench,
Okay.
which is designed to test an LLM's ability to handle diverse real-world JSON schemas.
So it's like taking a deep dive into JSON.
Yeah, it's like AIML's tougher, more specialized cousin.
So this focused benchmark helps us understand the strengths and weaknesses in more detail.
Exactly. In fact, Google's Gemini was evaluated using JSON Schema Bench, and while it scored nearly 100% on JSON validity,
Wow.
the benchmark revealed some interesting insights into its efficiency and how it handles those super complex schemas.
It's amazing how these benchmarks are helping us learn more about LLMs.
Yeah, and thanks to these efforts, we can actually track the progress in this area with incredible precision.
That's really cool.
As those models and techniques like constrained decoding and reinforcement learning keep getting better, we can expect those AIML scores to climb, leading to a future where LLMs consistently deliver that structured data we need.
A future I'm excited for, but I know things are rarely perfect in the world of technology.
You got that right.
Even with all this progress, there's got to be situations where things go wrong.
Yeah, that's where those pesky edge cases come in.
All right, well, we'll have to dive into that in the next part of our deep dive.
Sound good?
But for now, we'll take a break, and we'll be back soon with more on the world of structured outputs.
Looking forward to it. Welcome back to the deep dive. We were just about to get into those edge cases, where even the most carefully crafted schemas and techniques might not be enough.
Right, because it's easy to imagine an LLM spitting out simple JSON.
Yeah.
But what happens when you need it to generate something way more complex, like the HTML for a website?
Right.
Or the code for some financial algorithm?
That's where things get a little bit tricky. One common pitfall is just schema complexity. Imagine you're building the website with like hundreds of elements.
Yeah.
Nested structures, like you've got product carousels and drop-down menus and interactive forms.
Right.
Even with a well-defined schema, it's easy for the LLM to kind of get lost in the weeds and maybe accidentally omit a crucial element like this closing tag for a navigation bar.
So it's like asking the LLM to build a house with 1,000 different pieces and it forgets the front door.
Exactly. And the result is a broken website, frustrated users, and a lot of debugging for the developers.
Yeah, not a good situation. And I imagine it gets even more complicated when you're dealing with schemas that are ambiguous or poorly defined.
Absolutely. Ambiguous schemas are like recipes with missing ingredients or vague instructions.
Okay.
Even the most skilled chef would struggle with that.
Right.
And LLMs are no different.
So it's not just about having a schema, it's about having a good schema.
Precisely one that's clear, concise, and leaves no room for interpretation.
So it's like crafting a legal document, every comma matters.
Exactly.
But even with a perfect schema, are there other limitations? What about those trade-offs between control and performance?
That's a great question. It really gets to the heart of some of the practical challenges. So some techniques, like constrained decoding,
Yeah.
can be super effective at ensuring a valid output,
Uh-huh.
but they can also slow down the generation process.
Okay.
It's like having a meticulous editor.
Right.
They catch every error,
Uh-huh.
but it takes them a while to get through the whole document.
So it's that trade-off speed versus accuracy.
Exactly. We
Oh.
might get a perfect output,
Yeah.
but we might have to wait a bit longer for it.
And for some applications, that real-time performance is critical.
Right. Think of a chatbot
Okay.
that needs to respond instantly to user queries.
Yeah.
If we put too many constraints on it,
Uh-huh.
the conversation is going to feel slow and clunky.
And reinforcement learning, I imagine that adds some computational overhead as well.
It does.
So it's all about finding that balance.
Yeah, finding that sweet spot between control performance and resource constraints.
Okay, so we've talked about the challenges and the trade-offs, but I'm also curious about how structured outputs fit into the bigger AI landscape.
Okay.
How do they compare to other approaches like symbolic AI or those neurosymbolic methods?
That's a really interesting question. It gets to the heart of how structured outputs are shaping the evolution of AI.
Okay.
So symbolic AI, for example,
Mm-hmm.
it's all about using explicit rules and logic
Right.
to represent knowledge and solve problems.
Okay.
It's been around for ages.
Yeah.
Proven track record in areas like expert systems.
So if you need to be absolutely sure your data is structured in a very specific way,
Yeah.
symbolic AI seems like the way to go.
It can be, especially for tasks that involve those well-defined rules and relationships, but it's got its limitations. It can be pretty rigid
Uh-huh.
and often struggles with the ambiguity and nuance of natural language or real-world data.
Right.
It's like trying to fit square pegs into round holes.
And that's where LLMs come in with their ability to learn patterns.
Exactly.
So how do structured outputs bridge the gap between those two worlds?
That's the really cool part. Structured outputs allow us to introduce some of the rigor and predictability of symbolic AI
Okay.
into the more flexible world of LLMs.
Mm-hmm.
It's like adding scaffolding to a creative project,
Right.
providing structure without stifling creativity.
So it's not about replacing symbolic AI. It's about enhancing LLM.
Exactly, and that's where neurosymbolic AI comes in.
Okay, that's a pretty cool area.
It's this really exciting field trying to bridge the gap between neural networks and symbolic reasoning.
It sounds a bit like science fiction. Are there actual practical applications of that today?
There are, and they're becoming more common. Some approaches involve incorporating formal logic constraints
Okay.
directly into the training or inference pipelines of neural networks.
So you're teaching the LLM to think like a logician.
Exactly, while still letting it learn from data.
So it's not just about pattern recognition. It's about understanding the logic behind those patterns.
Exactly. And techniques like constrained decoding actually have a symbolic flavor to them. By imposing those grammatical rules on the LLM,
Yeah.
we're essentially injecting symbolic logic into the system.
So could you say that structured outputs are a stepping stone toward more powerful neurosymbolic systems?
I think that's a great way to look at it, by figuring out how to combine neural networks with symbolic constraints. We're opening up so many new possibilities for AI.
It's like building a bridge between these two different islands of intelligence.
I like that.
But before we get too carried away with the future, let's take a quick step back to the past.
Go ahead.
And think about those more traditional approaches to data processing, with those regular expressions and rule-based extractors.
Ah, yes, the trusty hand tools of the data world.
Reliable, but maybe a bit cumbersome.
Yeah, so how do they stack up against these structured output approaches? Are they still relevant?
I mean, they must have their place.
They do, especially for those simpler tasks or very structured data. But they tend to be pretty brittle, especially when you throw in the complexities of natural language.
Yeah, like trying to build a skyscraper with just a hammer and nails.
Exactly, and maintaining all those intricate regular expressions
Oh, yeah.
can be a real nightmare, especially as the data changes.
It would be a headache.
And that's one of the big advantages of structured output approaches.
What is it?
By enforcing structure during generation,
Mm-hmm.
you eliminate the need for all that post-processing and the maintenance burden that comes with it.
It's like baking a cake with all the right ingredients from the start.
Yeah.
We've covered a lot of ground here, from schema complexity to neurosymbolic AI.
We have.
But there's one more crucial aspect I think we need to discuss: security.
You're absolutely right. Security is paramount, especially as LLMs handle more and more sensitive information.
And that's what we'll be diving into in the next part of our deep dive: how structured outputs can help us build a more secure future with AI. Welcome back to the deep dive. We've been exploring the world of structured outputs. You know, these digital guardrails that are helping us shape the future of AI.
Yeah, it's been quite a journey.
It has. And before the break, we were talking about the security implications of all this. You know, it's one thing to have an LLM that can format data nicely.
Right.
But it's a whole other thing to make sure that data is accurate and reliable and protected from attacks.
Absolutely. Security is paramount, especially as we're entrusting these LLMs with more and more sensitive information.
Okay, so we touched on this earlier with injection attacks, but I want to unpack this connection between structured outputs and security a bit more.
Sure.
How do schemas act as a line of defense?
Well, think of a schema as like a really selective bouncer at a club.
Okay.
Only the data that meets those very specific criteria outlined in the schema
Yeah.
is allowed in.
Right.
So any malicious code or corrupted data that tries to sneak in, it's immediately flagged and rejected.
So it's like a digital immune system constantly scanning for anything that doesn't belong.
Yeah, that's a great way to put it. And this kind of protection is so important when you're dealing with things like financial transactions or personal health records.
Right, where a single error could have huge consequences.
Exactly.
So beyond those accidental errors or corruption, how do schemas protect against those deliberate attacks, the injection attempts?
So imagine an attacker trying to trick an LLM into revealing confidential information or running some harmful code.
Okay.
They might write a prompt that seems harmless,
Uh-huh.
but it has hidden commands designed to exploit the system.
So it's like a Trojan horse hiding a dangerous payload.
Exactly, and that's where schemas can help.
Okay.
By defining the exact format and structure of what's allowed.
Yeah.
The schema acts as a shield.
Okay.
It stops those commands from being executed.
So it's checking every line of code, every data entry.
Yeah, making sure it follows the rule.
And that makes it much harder for attackers to get through.
Much harder. And while it's not a perfect solution, it's a really important layer of protection.
It's like having multiple locks on your door.
Exactly.
And it's not just about external threats, right? Structured outputs can help us address internal risks too, like bias in the data.
That's right. We've heard so much about AI systems perpetuating bias,
Yeah.
but structured outputs can actually help us mitigate that.
Oh, so.
It's all about transparency and control. So when you define a schema,
Yeah.
you're making the structure of the data and the relationships super clear.
Okay.
And this makes it easier to spot those potential biases.
So it's like shining a light on those hidden biases.
Exactly. And once you see them, you can start to address them.
By maybe adjusting the training data or tweaking the algorithms.
Exactly.
It's a way to make these AI systems more fair and accountable.
For sure. And it highlights how important ethical considerations are
Yeah.
throughout the whole AI development process.
Well, it's clear that structured outputs are much more than just making data look neat.
Right.
They're essential for building a secure and trustworthy and responsible future with AI. But I'm curious about what's next for this field. What are some of the things you're excited about?
One thing that's really cool is adaptive schema evolution. You know, we touched on this before, but imagine LLMs that can actually update their own schemas
Oh, wow.
as they learn and encounter new information.
So it's like they're constantly refining the blueprints.
Exactly. And that's key for creating those truly intelligent and autonomous AI systems that can adapt to the real world.
It's like giving the LLM self-awareness.
Right, allowing it to reflect on its own knowledge.
Yeah.
And refine how it thinks about data structure.
And that could lead to some pretty groundbreaking applications.
Absolutely. AI systems that design experiments, analyze data from tons of sources, maybe even come up with new hypotheses.
Wow, so we're talking about AI that's not just processing information, it's shaping its own understanding of the world.
Exactly. And another thing I'm really excited about is integrating structured outputs with those external knowledge bases.
Okay, yeah, we talked about that with hallucinations.
Yeah, but it goes way beyond that.
In what way?
So imagine an LLM that can not only generate text, but it can fact-check its own output,
Okay.
draw inferences, maybe even make connections that we wouldn't see right away.
It's like having a super intelligent research assistant,
Exactly. And this could be huge for fields like education, law, medicine.
where having the right information is so critical.
Exactly.
It's an inspiring vision of the future, but of course there are still challenges.
Oh, for sure.
What are some of the hurdles that researchers are facing in this field?
One of the biggest ones is finding those robust and scalable ways to deal with ambiguity and uncertainty.
Okay.
Real-world data is messy,
It is.
and LLMs need to be able to gracefully handle those situations where information is missing or conflicting or just unclear.
Right. It's like teaching an LLM to navigate a world where the rules are always changing and the map is never complete.
Exactly, and that requires a level of flexibility that we're only starting to explore.
It's a fascinating challenge, and it's going to drive a lot of innovation.
Absolutely, and as these technologies evolve, we need to keep those ethical considerations in mind. We have to make sure these tools are used responsibly and for the benefit of everyone.
Well said. It's a good reminder that the future of AI is not set in stone. It's something we're all shaping together.
I agree.
And to our listeners, if you want to learn more or share your thoughts on this topic,
Yeah,
connect with us on social media. We'd love to hear from you.
thanks for listening.
This is The Deep Dive signing off.